Welcome back, folks. If we could please start quieting down and finding our seats. We're going to get started with our next speaker, Hans Herbach from ECMWF. Just a note to the speakers, I'm going to give you a 2-minute warning, and then I'll stand up at 15 minutes. So your 15 minutes is for you, how you'd like to use it. If you want questions, saves the time. Thanks, Hans.
Good afternoon. I'm Hans Herbach. I'm the leader of the Copernicus Climate Change Service Reanalysis team, which is performed at ECMWF. So, we are 7 people, and our main activity at the moment is the production of the ICR5 reanalysis, which is the state-of-the-art reanalysis, atmospheric reanalysis that we're talking about in this presentation. So I will present an overview first of what kind of reanalysis products there are at ECMWF, have been produced in the past, just to give an idea. Then I will go to ICR5, which is a follow-up of ICR Interim. I will talk about the configuration of ICR5 and also the status of ICR5, where are we now. Then I will show some results of ICR5 performance, and I focus mainly on comparison with ICR Interim, and then some final concluding remarks. So we have a long history at ECMWF on creating reanalysis data sets. So it all started back a long time ago with FIGI, ICR15, ICR40. Now we have ICR Interim as our main atmospheric reanalysis, but we are also now producing ICR5 to follow up. And it's the 5th in the row, so that's why it's called ICR5. But besides that, we have ocean reanalysis. We have, with respect to the ICR 2 FP7 research projects from the European Commission, we have produced centennial reanalysis like 20CR at NOAA. And so the latest version is 020C. Patrick will talk about that, and he has a presentation on that, and that also goes via coupled. So CERA-SAT is like ICR20C, but then using the full observing system. At ECMWF, we're going towards a coupled Earth system, so this is the first step. ICR5 doesn't have that yet, but the follow-up, ICR6, it should have that. And there's enhanced lens products. ICR5, ICR Interim Land, there will also be ICR5 Land, ICR5L. It will have a higher resolution, 9 kilometers. And we have atmospheric composition reanalysis. And the current reanalysis being produced also within Copernicus is the CAMS reanalysis. And Angelicum will give a presentation on that. In this conference, there's several of these products will be discussed in either presentations this week or in posters. Okay, so, but I will talk mainly about ICR5. So, as I said, the production of ICR5 is part of C3S. This is our website. Reanalysis, as Adrian showed, ICR Interim have tens of thousands of users all over, from many different disciplines. And we ourselves are users of reanalysis as well, of course. So one example is we produce these monthly updates of the climate, typically around the 5th of each month. We produce the state of the climate of the last month, and that's based on reanalysis. Currently, that's ICR Interim, but once we have the 3rd-year climatology, which we need to be able to tell whether there are anomalies, this will be replaced with ICR5. And ICR5 will also provide ECVs, essential climate variables, in the C3S Climate Data Store. And the Climate Data Store is the portal, the data portal, which we will provide the climate data. And ICR5 will be an essential part of that as well. Okay, so configuration of ICR5, how is it different from ICR Interim? So the periods we are producing 1979 onwards like ICR Interim, but in 2018, next year, we will have another stream or a few streams going from 1950 to 1978. So in total will be about 70 years of reanalysis. Then we have parallel streams, typically 1 per decade, but for the 80s and the 90s we have 2 per decade because we had some initial issues with the simulation system that we were a bit delayed, but now we have two streams of 5 years each, just to speed it up a little bit. We're using a model which was operational in 2016, but though at a lower resolution. We have better boundary conditions for greenhouse gases, volcanic eruptions data, volcanic sulfate, etc. It's all based on CMCC5 forcing. And we have used the Halley acid to sea surface temperature and OC-sub reprocessed sea ice products. And for near real time, we're using the operational Ostia products. The spatial resolution is much higher, 31 kilometer instead of 79. We have more levels, up to 1 Pascal. But it's not only that we have there more levels, we have more levels also in the troposphere and in the stratosphere. And another novelty is based on an ensemble. So we have we have a high res, but we also have an ensemble, which gives us uncertainty estimate, and we didn't have that in ERA interim. ERA5 land will be a separate component at higher resolution. There's a poster by Hawking on that in this conference. Then we did a user survey, and one of the things came out that people, they want hourly data. So that's what we do. We provide hourly data for ERA5. And of course, that becomes a very big data set. And if you add it up from 1950 onwards, hourly, 137 levels, 31 kilometers, you end up with 9 petabytes. So it's a really big data set. We use extra observations, a number of reprocessed climate data records. One example is for ozone. My colleague Cornell, he has a presentation on Wednesday on that. And we are able to use the latest instruments. And we have some extra features for variational bias corrections. For radiosondes, for instance, in ERA interim there was an offline determined scheme by Leo Heimberger, and he has now made an updated version for that, which we use in ERA5. Okay, so hourly data. I don't know, can we show the animation perhaps? How do I do that? How can I start this animation? So one of the features of what is new in ERA5, just to show you what the extra value is of the hourly data. Is it possible to start this animation? I don't know how to do this. No. The animation not working. But here you can see what the effect is of hourly data. You have really nice, you can the timings of precipitation is much better, much more realistic. You have much more detail, and it really makes sense to do hourly timely resolution. Then the uncertainty estimate. So we have it's reanalysis data. It's very convenient for people, for many users, because you have data everywhere for every grid point, every hour, every location, time. You have it. But people don't always realize that at the end of the day it's based on, here you can see the evolution, it is based on observations, and when you go back in time you have less observations, and therefore the quality of the product is lower, and that's why you want to have this uncertainty estimate. You can see that here in 1979 on the southern hemisphere there's much larger uncertainties than there are in July 2014. There will be a presentation by my colleague Andras on this on Wednesday, I think on Wednesday. Okay, so that's also extra important information. Then where are we? So we have released 2010 to 2016, publicly available. Then we have produced much more, and in 2018, beginning of 2018, we will start to add more segments. And also 2017, we have that as well. We're running 3 days behind near real time, but we will make that available as well. And also, there's one product which will be running 1 week behind near real time, we'll make it available. And as I said, in 2018, we will start the integration of the ERA5 segment from 1950 onwards. So it's not only the model data that we make available, it's also the observations. And we have tools like the Observation Feedback Archive in the Climate Data Store Toolbox, which allow people to easily to browse through the observations. And we also have a climate monitoring facility, which allows people to look at quick time series of reanalysis products. There are 2 posters on this in this conference as well. So how well does ERA5 perform? So I have two examples. I have ERA interim, ERA5 in the middle, and ECMWF operational model. This is now the mean precipitation for or average over the entire September 2017. And you see much more detail than you see in ERA interim. It's not as good as a high-res ECMWF operational system, but it's more towards operations than it is towards ERA interim, which is a very good sign. Then another example is Hurricane Harvey. The 5-day precipitation in the Houston area, well, recorded was about between 1 meter and locally up to 1.5 meters. ERA interim has much lower values, while ERA5 has up to 1 meter precipitation, and our operational system has about 1.5 meter. Okay, but that we can afford to go 70 years backwards in time because it's very high resolution. Then comparison to independent observations. So the troposphere looks all very, very good. This is one example of the partial statistics. Here you can also see where we are. So 2010, 2017 is what made, 16 is what made available, but we have produced much more in the meantime, but it's not yet available. It does look much better than ERA interim. But when you go to the stratosphere, and Adrian already showed something, is that we have, there are some things that we don't like. This is now at look, the scale is not that large, about 0.2, 0.4 Kelvin, compared to radiosonde data. And it appears that the radiosonde data, where you don't have the GPS RO data, ERA interim is not, ERA5 is not able to use those as anchors as effectively as ERA interim could do. And I don't have time to explain why that is, but again, there's a poster about this in the conference. And finally, when you go to the surveys again, go to ocean waves, ERA5 looks much, much better than ERA interim. This is a comparison with independent buoy data. So these data have not been assimilated. Okay, so summary. ERA interim is, by the way, this on the right is a presentation of forecast scores of ERA5. So we produce, these are the forecast starters from the analysis project. We do that for ERA interim and for ERA5, and when you compare the two, you see that better analysis gives better forecasts. So this is a kind of a way of also independently giving an idea of performance. And ERA5 is doing much better than ERA interim. So this for Z500. So as part, so ERA interim is 10 years old. I need replacement. It's as part of C3S, the production of ERA5 is well on the way. It's higher resolution. We have parallel streams, public release of 2010-2016. Other streams will be done in stages. The performance is very promising in the troposphere, although we have some imperfection as well, for instance, in the stratosphere. And the follow-up of ERA5, ERA6 is benefiting from the coupled Earth system we're going towards at ECMWF. And CRSAT will be the first, we will use that as a first step towards ERA6. Thank you very much.
Time for a question or two. All right. Maybe I'm getting a little ahead of myself. Oh, we got one.
Thank you. Based on these first results on the stratosphere that you are showing, you would not suggest to use ERA5 for estimating trends in the stratosphere? Estimating linear trends in the stratosphere with ERA5.
Yeah, well, it's of course the magnitude is not that high. It's about 0.2, 2.4. So I think the trends are larger. Mm-hmm. Yeah.
Yeah. Okay, but it depends on the region then, and yeah. Okay.
As there wasn't another question, I could also comment that there's a good 10-year overlap while we have GPS RO data from 2006 onwards. So it should be possible to actually merge ERA interim with ERA5 over this period. So one could use ERA interim and then merge it into ERA5 for trend analysis in the lower stratosphere at least.
We have to move on. very much, Hans. Yeah, thank you. The next speaker is Anarita Mariotti for NOAA.
Hi, everyone. It's a pleasure to be here in this wonderful place. My name is Anarita Mariotti. I work for NOAA in Maryland, in Silver Spring. And what I'm going to talk about today is some research that's going on as part of the MAP program, the Modeling, Analysis, Predictions, and Projections program, on reanalysis and Earth system data simulation. And so I'm really going to focus on research rather than production of reanalysis. And there is a lot more work that's done on research at NOAA beyond what I'm going to be talking about here as part of the NOAA OER labs. So first I'm going to talk about the MAP program. So the MAP program, the Modeling, Analysis, Predictions, and Projections program, is a NOAA research competitive grants program. So you can write grants and get your projects on reanalysis and data simulation funded if you're lucky, if you're good. So we are interested in advancing NOAA's global coupled modeling, predictions, and projection needs. And we all coordinate with other programs at NOAA, different line offices at NOAA, and also outside of NOAA with our colleagues in the US, other US agencies, and also internationally via the World Climate Research Program and also the Weather Climate Research Program. So we support research and development as well as transition activities, so those activities that really support the enhancement of the services that NOAA can provide via the climate test bed. So here you can see a set of sort of activities. So we don't just do reanalysis and data simulation, although this is what I'm going to be talking about today. We do research on predictions weeks to decades. That's our scope. We do modeling applications. Drought has been a primary focus. We're now moving to also other applications, climate Earth system modeling and climate projections. Again, as I anticipated, we support the advancement of the NOAA suite of models for Earth system monitoring and predictions week 2 and beyond. So in terms of areas of support under this priority, as I said, coupled Earth system data simulation for monitoring prediction has been a major focus. And in particular, we have organized the Climate Reanalysis Task Force that I'm going to talk about more in a second. And then more generally, in the context of modeling, experimentation with high-resolution modeling, advancing physical representations in models. We have organized climate process teams together with other US agency colleagues. We are advancing process-level model diagnostics. So we also have a group there, a diagnostic task force that's looking at that kind of stuff, and also supporting modeling software infrastructure and data access. So in terms of what we have done in the past, so our past work has really focused on climate reanalysis or atmospheric analysis as a follow-up to the CFSR effort. So when that was released, we supported work to evaluate the CFSR as well as other reanalysis that had been released around about the same time. And so that research gave rise to several questions, sort of high-level questions that were addressed by our projects, and including, whether accuracy of reanalysis depicting as accurately as possible a given state of the atmosphere and long-term homogeneity can really be balanced in a single reanalysis data set that can be used for both monitoring and prediction. So here are two sort of sub-questions, how to deal with data discontinuities and inhomogeneities, as well as how to maximize the use of available observations to maximize accuracy. A big issue is how to deal with model biases. So if your model has an error, you can give it the best observations, and when you do DA, it will kind of pretty much reject them. So we put in some effort to try to improve the models that NOAA uses for data simulation, and also clearly what is the best method for data simulation is another question that was raised. And also, what is a viable methodology for creating reanalysis in separate streams? These are some of the research questions that were raised after the CFSR. What we did, we initiated a set of projects in fiscal year 13 through 15, and some of them are actually still ongoing. We funded several projects for 3 years to evaluate and improve aspects of NOAA reanalysis, and here I'm talking about atmospheric analysis primarily, for climate monitoring and prediction. And this group was actually led by Gil Compo, who's sitting here somewhere, as well as other good colleagues from NOAA and outside. And it worked very well to coordinate the project that we initiated. Here you can see some of the projects that were involved in this effort. So an umbrella project led by Kumar and Compo to kind of do experimentation on different ways that you can do climate reanalysis, different types of setups, also for different purposes and periods of time that need to be covered. And then as well as a set of projects that focus on specific issues that were found in CFSR, so the stratosphere, trying to improve the stratospheric representation in the NOAA reanalysis, advancing data simulation in the ocean component, evaluating air-sea fluxes in the reanalysis, improving the land data assimilation, evaluating how clouds are represented in the clouds, precipitation, radiation represented in the polar regions, and again also looking at stratosphere and in particular ozone issues. So as I said, this task force worked very well for 3 years, and at the end of their lifetime, they organized a workshop. That's a picture there. It was actually an open workshop where a lot of people from also Europe and other agencies came to work with us to discuss, what is going on in different centers, what are the complementary efforts at national and international institutions, and also talk about challenges and possible solutions. So we greatly appreciated that participation. And there is a report that came out of that workshop that's available for anybody who would like to take a look, that it summarizes basically where they landed with these projects and the issues that were highlighted. After that, we started some projects to try to sort of improve specific aspects of the NOAA system that's used in the Weather Service. So we have currently 4 projects that focus on 4 particular improvements: ocean, waves, land, and ice. So these are just more specifically what they talk about. So there is looking at hybrid global ocean data simulation in replacement of GODAS, trying to integrate a coupled wave ocean system in the Weather Service system, land updates, and also sea ice. So that's for what we have already, the projects that we have either carried out with our PIs or are just ending now. And now what's next? So what are the kind of questions that we think we need to address? So this is to give you a background, what's going on at NOAA and why we're doing what we're doing. So it's a busy plot, but given to me by, actually it's cut, the slide is cut by Brian Gross, who just started as a EMC Weather Service Director. So they're going through a process where they want to sort of simplify the NCEP modeling suite, and this is strategic vision for how they plan to do that. So they're aiming to go from is this a pointer? Oops. Aiming to go from a, oh, okay, this one, okay, cool. All right, from this busy sort of kilt, they call it, of products and systems to a much more sort of a simplified system where really the products really drive what the system need to look like. So starting from the kilt of models and products, created by implementing solutions, so basically tool they had, to a system that's product-based and covers the present elements of the production suite in a more systematic and efficient way. So this is clearly something that takes time. This is a forklift change in their system that's going on there. They're evolving towards a unified modeling and data simulation system. So here you can see the components of this system. Sorry. This doesn't seem to work very well. Where you have a system that goes from hour to day to week and month and year predictions, and then a UDA, unified global couple model and data simulation system that would kind of work for this whole suite. So it's a big undertaking that's going on there, and will include also pre- and post-processing calibration, verification, and validation. So as part of that, reanalysis and reforecasts are planned. So this is basically something, it's a long-term project that's going on, and we, as a research program, we want to support this effort. Really, one of the drivers, as I mentioned, is really this change that the Weather Service is undertaking towards an Earth system monitoring and prediction system that's going to be put in place in the next 5 to 10 years, probably less, hopefully. So another driver is just looking at the data simulation research gaps that were highlighted by the community and also the project we put in place. So, for example, how do you do data simulation in the best way? How do you maximize the use of the data you have? How do you move towards our system data simulation? A lot of interesting questions that we want to address. And also supporting the research that can be done through advancing coupled DA. So specific areas of interest that we have are new data simulation approaches for Earth system monitoring and prediction, systematic exploration of benefits of weakly versus strongly coupled DA, so again on the data simulation methodology, and also incorporation of your observational data sets from NOAA. And we recently had a meeting with our GPSS colleagues to discuss the use of the data that's coming out of those systems and how we can potentially best exploit them for reanalysis data simulation. So this is basically what we have right now put in place. We have a research call on Earth system data simulation. And our partners are GPSS and also the Weather Service and GGPS program. And this call has two foci, and I know some of you here actually have proposals in this call. So we hope to have some good proposals looking at methodologies for coupled data simulation of relevance to Earth system prediction and or monitoring needs of NOAA. And things that the background for these are really to consider the fact that there is this evolution towards a unified data simulation framework for the Weather Service, which will include having a unified sort of data simulation effort, so a joint effort for data simulation integration, JEDI. Many of you may know about this. And the second foci, sorry, I miscalculated there. So it's really having newer experimental DA approaches to developing new monitoring products for the cryosphere, ocean, land, or atmospheric composition. So using climate quality NOAA data and also reprocessed data specifically from GPSS. And we currently have proposals in review. Hopefully they will start next summer. Yep. So this is my summary, and I think I'm going to just leave it at that. Thank you.
Thank you very much. Next up is Ron Gilero from the GMAO. Let me say that on here. Next is Ron Gilero from the GMAO.
Check. It's pretty dull. I can try and find batteries. you want me to just start then? Yeah, go ahead. Okay. Good afternoon. As many of you know, and Adrian mentioned, NASA and the GMAO have been very active in reanalysis for quite some time. We have several people here who will be giving presentations and posters on a lot of that work. What I'd like to take today's, we have a monitor here. What I'd like to take today's, this talk for is to really discuss what we're doing to extend our core GEOS forecast assimilation systems to encompass more components of the Earth system, coupling. The process is to progress incrementally through a combination of systems with increased level of coupling. We've already begun this work, in addition to offline component analyses being driven by the atmospheric analyses for what I call emerging capabilities, which I'll show some examples of. A point to make is that the work that we're doing in reanalysis in GMAO is really tied to NASA's big investment in Earth observations. These products linked the instrument teams, the use of the data in Earth system analyses to show their value beyond just the observations themselves, as everybody in this room knows that you learn a lot more from the observations by including in models, and planning for new missions. As I mentioned, this talk focuses on just a few examples of some of our current capabilities and pathway to this coupled system. Okay, so this is the same kind of slide that Hans showed, just showing a timeline of the reanalyses that we've produced and the reanalysis products. Most of you are familiar with MERA and MERA-2, the atmospheric, complete atmospheric reanalyses, but these have also driven what I call some of these component reanalyses to look at new capabilities. There's an MERA ocean-driven analysis, aerosols, land, and then these developments some of these get folded into the next more complete reanalysis. In particular, what we did in terms of the land forcing and the assimilation of aerosol observations went into MERA-2. That will in turn be driving new component reanalyses planned in the near future. Sometime in the next year or two, we'll be producing a new MERA-2 ocean reanalysis. That will be also a prep for our seasonal forecast system, and we're starting to do some chemical analysis as well. Looking a little bit further downstream, sometime after 2020, we're hoping to produce a more coupled atmosphere-ocean analysis to include aerosols and sea ice, and I'll touch on that a little bit more. Some aspects of MERA-2, I won't spend much time on this because there are a lot of posters and talks about it, but I would just mention a highlight. This is our most recent atmospheric reanalysis. It has some advances over MERA in terms of the number of observations, some of the modeling and analysis updates, but in particular, the focus in MERA-2 is on these non-meteorological aspects, what I'm talking about here, as a pathway to more complete reanalysis. Among those was the aerosol data assimilation, cryospheric processes, and the use of observations for NASA observations in the stratosphere. This is well documented. There's a special collection of Journal of Climate. I just wanted to highlight one result, which was, one aspect, which was the aerosol analysis that was done in conjunction with the atmospheric analysis. This was, at the time of MERA, we were analyzing 15 species. That's now up to 17, including nitrates in our real-time forecast system. This is just an illustration of some time series of total aerosol optical depth in the black, and then that broken down into some of the component species for various regions. Southeast, you can read them, South and East Asia, North Africa and Atlantic, and Amazon Basin. So you can see the variability. Globally, you can see the seasonal cycles of dust and biomass burning in all regions, the large volcanic eruptions. So in here, you see the gray color is sulfate, which is typical of the prominent in the volcanic eruptions. As you look more seasonally, you can see, for example, over North Africa and the Atlantic, it's dominated mostly by dust. And then over the Amazon Basin, you see the biomass burning. So that's just an illustrative example. There's more presentations on that. But looking ahead, a big thrust in our development right now is the development of a coupled air-ocean atmospheric data assimilation system. This is actually the coming together of two, up until now, separate development paths. One was the atmospheric data assimilation, which drives our NWP and reanalysis, is what I've spoken about so far. But in addition, we've undertaken recently an update of our seasonal prediction system. So at the moment, as of January and just recently in October, what I'm showing here are just the main components of our atmospheric data assimilation and our sub-seasonal to seasonal system. It's a 4D on VAR, 12 kilometer. You can read the main attributes. Over the next few years, we'll be increasing vertical resolution, and horizontal resolution and new physics. At the same time, we'll be introducing higher resolution into the seasonal system, the addition of new observations for salinity assimilation and sea ice. Somewhere after that, the production of MERA 2, and by 2021, we hope these systems merge into a coupled AO, atmosphere ocean assimilation system, which will handle all the applications in coupled. So here's my confusing diagram, just to give you a little more detail of what the coupled system will look like. The stress emphasis here is that it's a weakly coupled system. So you'll see all the components of the atmosphere. I'll talk a little bit more about the AO interface in a moment of the coupled GCM, but then separate analyses for the atmosphere, for the weather, the ocean, and the aerosols. The coupling will come through the background integration of the coupled model and the fact that we give the increment to the model in a 4D incremental analysis update. This is where the exchange of information occurs. So the first step of this is already in place in terms of a coupling. In fact, this is running in our current forecast system right now, is a semi-coupled SST skin assimilation. So in addition to just sort of the bulk, Reynolds, or ASTI SST, we do an analysis with surface-sensitive radiances of the first couple millimeters of the ocean surface. It uses a model diurnal cycle with a 2-meter mixed layer. It assimilates surface-sensitive obs, as I just talked about. And the bulk temperature that comes in at the base of this layer is from the data sets, ASTIA. But it does produce quite a bit of difference from the cool skin actually is quite different from what you'd use, say, from ASTIA. Can we click this animation? Oh, wait, is this one? Maybe I can do this one. Maybe not. Is there a bar there for you to, anyway, that's supposed to be animating. Is that working? If not, I'll probably need to move on for the sake of time. That's unfortunate. Okay, how am I doing, Mike, on time? Oh, okay, too bad we could have shown that. 5 before 15 or 5 before 10? 5 total. Okay, great. Just then I'll talk about 2 areas where we have emerging capability that was not necessarily in the path of the first coupled ocean atmosphere system that I mentioned a moment ago. Again, driven by NASA observations, we have an effort in ocean biogeochemical assimilation. The current system consists of the NOBM biogeochemical model, which is this big complicated thing on the left that I don't have time to talk about in any detail, with the spectral radiance model and the MOM ocean circulation model. It assimilates chlorophyll, absorption of CDOM, which is essentially like tea in the ocean. It's just organic model that colors the water. And carbon, it outputs a whole range of variables, chlorophyll, nutrients, different phytoplankton groups, and carbon fluxes. We can drive this with an atmospheric forcing, and in particular, we've actually used the MERA reanalysis to drive a longer what we call MERA NOBM, which was our first ocean biogeochemical analysis. This is just an illustration of the types of things you can produce. So we now have over 2 decades of high-quality ocean color observations. For example, in terms of NASA instruments from CWIPS and then MODIS and now VIIRS. But these give you total chlorophyll. But you know, a much nicer thing about the reanalysis, of course, is you get global coverage, which these types of ocean color instruments don't necessarily give you. But also, in the same way, with the aerosol analysis, you speciate the AOD. With the biogeochemical models, you can speciate the chlorophyll. So this is just an example from the MERA OBM of some decadal trends in the different types of chlorophyll. And you can see different changes, the total being a combination of changes that are quite different in the various types of phytoplankton. And each of these is quite important in the ocean ecology system. The diatoms feed the food chain. These tell you about the cyanobacteria, it tells a lot about sinks of carbon, and coccolithophores, I think I've got that right, tell you about the changes in pH in the water. So we're starting to analyze these kinds of trends. The last emerging capability I want to talk about is the chemistry. This is a long-standing collaboration we've had with Harvard to develop the GEOS Chem module in the context of GEOS. This has been going on for some time, but quite recently, as a research project, we began daily full chemical forecasts that run after our real-time NWP and uses that analysis and the IAU from that to drive the chemical forecast. These are running at 25-kilometer resolution. Currently, there's no assimilation of chemical species in this run. It's just getting going, but we hope to work that in time. And as you know, and you'll probably hear, there are observing systems coming that are monitoring air quality from the US, Asia, Europe, Tempo, Sentinel, GEMS. Can we start this animation? This is a current forecast. Oh, okay, there we go. This is a forecast actually from last night or the night before, just showing the forecast of NO2 over the last couple of weeks. These are 5-day forecasts strung together. The black is the verification for Zurich, which was the nearest station I could find for Rome. The orange and the yellow are the forecast progressing in time, the yellow later in the forecast, and then the verification from the station. And it's quite interesting. You see the breathing of the NO2 as it increases during the day. It very rapidly converts to nitrous oxide, and then it diminishes. But another interesting thing is you also see you also see the weekends here where there are not as many cars. It's quite interesting. And lastly, I'll just show, again, this is an animation of analyses of Health Air Quality Index, which is just, in our case, we use a definition. It's a Canadian definition which combines ozone, NO2, and PM2.5, and we produce forecasts of this every day. This is just an animation. Whenever you're ready, you can start this animation. That's quite a very interesting period in the last 2 weeks. It has the formation of Ophelia, which I'll get back to in a moment. It has the big fires in Portugal and in North America. And again, as you go from white to red, the air's getting worse and worse. But watch, Ophelia is quite interesting. The front kind of blocks the dust. Then it interacts with the fires in Portugal. You can see it sweeps into Ireland and produces this, what any of you living in the UK remember as this red sky phenomenon that happened a couple of weeks ago. So that was very nicely captured. Okay, I'll just summarize here quickly. Am I okay? Good. So the GMAO is working toward an integrated system, Earth system analysis to advance our activities in subseasonal to seasonal forecasting, reanalysis, and eventually NWP. A reanalysis with coupled components of the atmosphere, ocean, and cryosphere is planned in the at least to begin in the 2021 time period. There's a lot about this TBD, depending on how the research and development currently underway goes. Again, it will, of course, given our focus on NASA observations, which are quite plentiful for aerosol, chemical, biogeo, we'll be focusing research in those areas as well and hoping to integrate those into the system over time. In the meantime, we'll continue production of MERA-2 and these component-driven reanalyses that we'll use as test beds to inform the more coupled reanalysis. Thanks.
One question?
Oops.
Thanks. Regarding your biogeochemical reanalysis, as far as I understood it, you are assimilating only the biogeochemical data and not the physical, the ocean physical data, right? Is it? Yeah, only ocean color. Yeah. Is it? Can you explain why you decided to use only chlorophyll and not the ocean data? You rely on your ocean model?
Yeah, so of course you asked me one of the components I know the least about. I can't really tell you why it's only the ocean color. I assume it has something to do with the length of the record and how easy it is to assimilate it, but as far as I know, that's all that's being assimilated now. I don't know if anyone here could expand on that. Sorry.
Hi, Ron. I have a question about the method you're planning to use in your coupled system. Are you moving towards a strongly coupled system or not? Are you thinking to use more ensemble method, ensemble common method? Which way do you see it going?
So at the moment, there's no immediate plan to have an actually fully integrated coupled covariances in the ensemble, but the atmosphere is a hybrid 40 on VAR. The aerosol is actually an ENKF, it will be, and the ocean is an LETKF right now, but that will be an expansion of the ensemble that's actually in the GSI for the atmosphere. Thanks, man.
The next speaker is Shinya Kobayashi from the JMA.
Good afternoon, everyone. My name is Shinya Kobayashi. I'm leading the Japanese reanalysis group at JMA, and from now on, I'll be talking about reanalysis at the Japan Meteorological Agency. In this presentation, I'd like to mainly focus on the role of reanalysis in JMA's climate services, strengths and weakness of our current reanalysis, GEOS, and our future plan. First, I'd like to briefly explain the role of reanalysis in JMA's climate services. Climate services requires a homogeneous, high-quality dataset that covers a long period of time, and reanalysis provides such a dataset. One of the principal applications is the seasonal ensemble prediction system, which uses reanalysis data as an initial condition for a forecast experiment of the past period, or what we call reforecast, in order to evaluate the performance of the system and develop the forecast guidance. This is an important process for putting a new seasonal prediction system into operation. Reanalysis also provides a fundamental dataset for climate monitoring and extreme event analysis, El Niño monitoring, study of past severe weather events, and so on. Since reanalysis is used in a wide range of JMA's climate services, it's very important for us to continue the effort of improving the reanalysis in order to improve these services. JMA has so far conducted two global atmospheric reanalyses. The first one, GEOS-25, was produced with JMA and Japan's Central Research Institute of Electric Power Industry, which covers the period from 1979 onward. The second one, GEOS-55, was produced with a more sophisticated numerical weather prediction system and assimilated newly obtained past observation. It also extended the period back in time to 1958. It's been used in various JMA's climate services since its completion in 2014. GEOS-55 data are also provided to the public from JMA data dissemination system and cooperative organization, including NCAR. Just to give you an idea of how these data are used, this pie chart shows you a breakdown of work focus for users registered at JMA data server. As you can see, JRA data are used for various purposes, ranging from basic research on climate, weather, oceans, to practical applications such as agriculture and renewable energy. So now, I'd like to show you a couple of slides regarding strengths and weakness of JRA55. This slide shows you global mean temperature anomalies from the lower troposphere to the lower stratosphere for JRA55 and 3 earlier generation reanalysis. More specifically, JRA25, ERA40, and the NCEP-NCAR reanalysis. I also plotted the time series from 2 independent observational datasets for verification purpose, which are hardware center observational dataset and remote sensing system, microwave sounder observations. As you can see, earlier generation reanalysis have quite different variation and trend from the independent observation. JR25 in particular shows large jump in the lower stratosphere in the late 1990s, which corresponds to major changes in satellite observing system from TOPS to ATOPS. The cause of the jump is mainly due to the fact that radiative transfer models and bias correction schemes used for TOPS and ATOPS were different. In JRA55, on the other hand, we are using a single and more sophisticated radiative transfer models and bias correction scheme consistently for all satellite radiances. As a result, temporal consistency is considerably improved compared to JRA25. What this result suggests is that in order to produce temporally consistent reanalysis, it's very important to maintain the data assimilation system, which is, after all, the basic principle of reanalysis. However, even if the consistency of the data assimilation system is maintained, that wouldn't necessarily guarantee the temporal consistency if the assimilation system have a large bias. This is an example of such cases and shows you a time height cross-section of global mean specific humidity increment. Although JRA55 does not show as large impact of changing of observing system as JRA25 does, it generally shows moistening increments above 850 hectopascal and drying increment below that level, which is mainly due to the fact that the assimilation model has a dry bias in the upper and middle troposphere and a wet bias in the lower troposphere. And those biases are corrected by observation. The problem is that the moistening increment gradually increased as we assimilated more satellite radiances from water vapor channels. And as a result, JRA55 overestimates the increasing trend over those layers. What we learned from this result is that in order to produce the temporally consistent reanalysis, it's very important to reduce model biases, and it's also important to constrain model biases with more complete observation, for which recent effort of data rescue for early observation and recalibration and reprocessing for satellite observation would be very helpful. That result also emphasized that having a deeper understanding of model biases and impact of changing observing system is important for evaluating and improving temporal consistency of reanalysis. To this end, JMA Meteorological Research Institute produced 2 additional data sets. The one is reanalysis using conventional observations only, called GRA55C, and the other is AMIP type simulation called GRA55AMIP. These products are publicly available together with GRA55 at the GRA55 family. Now, I'd like to talk about our future plan. JMA is currently preparing for the next reanalysis called Japanese reanalysis for 3/4 of a century, or GRA3Q, with the aim of producing more improved reanalysis and contributing to climate services and climate research. In GRA3Q, we are planning to increase the horizontal resolution to 40 kilometers and introduce latest improvements from the NLP system. We are also planning to use high-resolution SST dataset based on the Professor Nakamura's research, which was presented earlier today. As for production schedule, we are planning to start the production in the first quarter of 2019. And one of the principal goals of GRA3Q is to reduce biases in surface fluxes, which are important variables to drive land and ocean models. This slide shows you the differences between surface net energy fluxes from the preliminary experiment for GRA3Q, GRA55, and the series OA flux dataset. As you can see in the bottom left panel, GRA55 shows large upward biases over the tropical oceans and large downward biases over the Antarctic Ocean. On the other hand, the preliminary experiment for GRA3Q shows much smaller biases over the tropical oceans, which is mainly due to the reduced errors in the solar radiation and latent heat fluxes. From such improvement, we expect that GRA3Q will be able to contribute to climate services and climate research. So that's all for JMA reanalysis. And this is just a word play. The 3Q is pronounced as thank you in Japanese. So thank you for your attention.
So, thank you very much for the talk. So GRA3Q uses high-resolution sea surface temperature. Does it use the high resolution?
I'm sorry. Could you say that again?
And see if I understood. One of the ideas was to use high-resolution sea surface temperature in this new reanalysis. Do you see the impact of using the high-resolution sea surface temperature in the surface fluxes, and is it improved?
Yes. Actually, this is the difference between surface net fluxes of GRA3Q and GRA55. And if you see the surface fluxes over the frontal region, we have actually big differences. And I think that's the benefit of using high-resolution SST dataset.
Okay, thank you.
One more? Thank you very much.
Thank you.
The next speaker will be Laura Slavinsky. speaking for the 20th Century Reanalysis version 3.
Cool, thank you. All right. Well, thanks for having me here and giving me the opportunity to speak about the forthcoming version 3 of the 20th Century Reanalysis. And this is the series NOAA Historical Reanalysis. So historical reanalyses, if you're unfamiliar with what that means, it's available back to 1851. Version 3 is going to be available to the present and will be kept up to date sort of as long as our system is going to be maintained. And the way we go back that far is that we're only assimilating surface pressure observations. We're assimilating this into an ensemble of model forecasts in order to provide sub-daily global atmospheric conditions, so every 6 hours. Now, version 3 will use the NCEP global forecast system at a resolution of about half a degree with 64 vertical levels, and that's up from 2 degrees and 28 levels in the previous version 2C. And we're using the ensemble Kalman filter as the previous version used, but now we have 80 members instead of 56 members, so we get a little bit better uncertainty quantification from our ensemble, as well as other improvements that we've worked on. Version 3 also addresses several issues and biases that were present in version 2C. I'm not going to talk about the biases in this talk from version 2C. If you'd like to know more about those, come to my poster on Wednesday, please. But I will talk about the improvements that are in version 3 that we've sort of worked on because of the issues that were in version 2C. The 3 improvements that I'm going to focus on in this talk are, firstly, our improved uncertainty quantification that we get from both a larger ensemble as well as these improved methods for localization and inflation. We also have an improved method to avoid numerical instabilities, which is a better data assimilation method, basically, and then a bias correction applied to marine observations prior to 1870. So we'll start with our uncertainty quantification. Because we have an ensemble method, this kind of lends itself very easily to quantifying our uncertainty. And essentially, we just look at our ensemble spread, right? As our ensemble spread is bigger, that means that we're less confident in our estimates. And when our ensemble is tighter, we have more confidence. And as we have more observations, as they become more frequent and denser in space, the confidence in our estimates increases, so the uncertainty decreases. And you can see this when we plot the ensemble spread versus the number of observations in time. This example is for sea level pressure over the US. And this is version 2C. But the process of assimilation, though, causes the ensemble spread to decrease too much sometimes. So this can result in overconfident estimates. And in order to ameliorate this, we basically inflate the ensemble. And this is a very conventional, traditional way, method that's used in the ensemble Kalman filter. So in version 2C, we used a prescribed inflation, basically. It was defined, it was a multiplicative factor. It did change in space and time, but it was prescribed ahead of time, basically. There are 3 time periods that it was set for, and then 3 spatial regions that it was set for. And this caused some issues, actually, in our uncertainty quantification of version 2C. So this is a map of what I'm calling confidence. It's 1 minus the ensemble spread divided by some climatological spread. So essentially, when the confidence is 0, our ensemble is as confident as climatology. So when our confidence is greater than 0, in the red in this map, then it's telling us how much more certain than climatology we are. And when it's blue, it's saying that it's less certain than climatology, which is not good because why wouldn't we just use climatology in that case? That's not really what we want. So obviously there's a little bit too much blue in this map, particularly in the Arctic. So it's too uncertain, and then it's too confident over the US and Europe. The inflation's not quite doing enough there. So in version 3, we're using an adaptive inflation algorithm. It's called relaxation of prior spread. And essentially, the amount of inflation is proportional to the amount of available observations at that time and place. So it can change a lot more, a lot better than just prescribing it ahead of time, basically. So when we have a dense observation network, for example, over the US and Europe, our inflation parameter is higher. And then, for instance, in the southern hemisphere, when we have very few observations, we have a much lower inflation. And we can see that this has really improved many of the issues that were present in version 2C. So now we're not too uncertain in the Arctic. We have more certainty there, and we have more spread over the US and Europe. So next, we have an improved method to avoid numerical instability. So very basic idea of what the Ensemble-Kalman filter does. It has forecast steps and analysis steps. And the very basic implementation means that these analysis steps sort of, you end up with this discontinuity because you're literally moving the ensemble members when you're assimilating an observation. And those discontinuities can cause gravity waves and instabilities and make your model blow up, which is not great. So version 2C used a digital filter to smooth these jumps out. And unfortunately, this had the unintended consequence of causing these artificial precipitation trends. So this is a map of, so we have our assimilation window is 6 hours. And we can look at the precipitation rate from hours 0 to 3, and then from 3 to 6. And we average over all assimilation windows, in this case over 6 years. And we see that there's actually a trend. So this is not a real trend. This is a consequence of this filter, basically. But it's also not small. So the global average, which is a little bit cut off, is 0.7 millimeters per day. But you can see in the tropics, it gets up to around 3 millimeters per day trend just from the filter. So that's kind of an issue. Version 3 uses the incremental analysis update that was mentioned in the previous 2 talks ago to avoid these instabilities, and also doesn't have the unintended consequence of this precipitation trend. So that's been improved. And then finally, we've bias-corrected marine observations prior to 1870. So if anyone who's familiar with version 2C, it had this pretty strong bias prior to 1870 from biased ship observations. So this is the sea level pressure anomaly in 1854 from version 2C. The global sea level pressure average was 1,009 millibars, which is about 2 to 3 millibars too low, probably. And you can see that from the climatology, it's blue all over pretty much. And this is due to biased ship observations, but also we were allowing the dry air mass to be updated. And so we end up with this sort of feedback where we're just constantly the ships are being allowed to pull the pressure lower and lower. So before I actually get to bias correcting the ships, what we're also doing in version 3 is no longer allowing our system to increment the dry air mass. So instead we're conserving it sort of as part of the model. It's just going to keep it fixed. We're fixing it at 98.3 kilopascals. And you can see just doing that without even bias correcting the ships, we've already improved the total global sea level pressure average is now 1,011.4. So that's what's cut off at the bottom there. So our global sea level pressure average is much more reasonable. We do have the obvious issue of the southern hemisphere that we're still kind of working on. But you can see overall it's much less blue. What you can see, because we're still assimilating the biased ships in this experiment, there's blue still where all the ship tracks are. So around the southern tip of South America, as well as in the Atlantic and Pacific Oceans, there are still some blue spots there. So if we now use bias-corrected ships, so we actually pre-process the ship observations on a ship-by-ship basis, calculating this bias from a climatology, we end up with an even better picture. On the right here, those blue spots around South America, for instance, have gone away. And the global sea level pressure average is still about 1,011 millibars. So, just to sum up, hopefully this was mostly just an advertisement for version 3 coming up. The 20th Century Reanalysis, all of them really provide a 150-year or more history of the global atmospheric state. The previous version 2C had several opportunities for improvement that we've taken most of those opportunities in version 3. But those biases, if you'd like to see more details about that, I have a poster Wednesday afternoon. The ensemble method that we use in the 20th Century Reanalysis provides a measure of confidence, and the new inflation algorithm in version 3 prevents over-tightening the ensemble when we have a lot of observations without giving too much spread when we don't have a lot of observations. And really providing a reliable measure of confidence is really important for assessing changes in climate variability. I mean, one of the reasons to have a historical reanalysis is to be able to see how these extremes are changing and how things are changing over a longer time period. But if we can't reliably judge the extremes and the probability distributions, then how can we use it? So having a reliable measure of confidence is really important. And then other improvements that we have in version 3 over version 2C, we have a higher resolution, better data assimilation algorithm, we're conserving the dry air mass, we're bias correcting ships, and there are many other improvements that I don't have a chance to talk about today, but I just hopefully get you all excited about version 3, which will be coming out shortly. All right, thanks.
It's time for questions.
So you said that you inflate the spread to simulate the fact, fact that certain regions are observed more than others. But I wonder whether you take into account also the fact that if you go back to the past, observation quality was different. So do you simulate the effect the observation quality, not just the number, but also the quality has changed throughout the 150 years?
So the inflation factor is determined by how assimilating the observations would improve the estimate. So I think it kind of can in a certain way. What we're not doing is changing the observation error in time, which we could be doing that, but aren't doing that. So.
Hi. In this long 20th century reanalysis, model error is a factor. So do you have any plans of treating model error explicitly within the ensemble generation?
Within the... yeah. I mean, we have a stochastic model. But other than that, no specific plans that I can think of. Yeah.
Could I make you a small question? What are the increment, the improvement that you find using the Kalman filtering? I don't know if this is...
Over the improvements from the ensemble Kalman filter over like variational 40 bar or... I mean, so we haven't run our system using anything other than the ensemble Kalman filter, so I can't give any specific answers to that.
Okay, thanks.
Yeah.
The next speaker is Shiquan Liu, talking to the Chinese Meteorological Administration reanalysis. Here you go. Forward, back.
Okay. Good afternoon, everyone. I'm Jake Liu. I'm going to present CMA's reanalysis efforts on behalf of many scientists contributed to this work. Some listed here, some is not listed. Go next. Okay. So a little background about CMA's reanalysis. That's the first time CMA conducting this global reanalysis. So this work is started in early 2014, led by the National Meteorological Information Center of CMA, and include both atmosphere and land component. And there are, in addition to this lead NMIC, and also have 3 other CMA national centers, and also 3 other outside institutions involved, including this NMC, NSMC, this climate center, and also some 2 universities and the research institute. So the goal is to produce a 40 years global reanalysis. This with grid resolution about 30 kilometer and a 6-hourly interval. And also, it was planned to use a hybrid variational ensemble technique. So it potentially will also provide uncertainty information for this atmospheric part. And then after this 40 years reanalysis from 79 to 2018, the system will then be continuously running for this climate monitoring purpose in near real time. Okay, so we pretty much keep the track of original planned timeline. So first couple years is mainly focused on the collecting and processing observations, conventional data, satellite data, and also experimenting, data simulation and modeling system. Originally, it was planned to use the operational NWP system in CMA. In 2014, at that time, CMA used a version of spectral model based on a quite older version of NFS, and plus the older version of NOAA's GSI 3D VAR system. And after some experimentation in the first 2 years, it was found, because it's some quite older modeling system, even though we updated data simulation system from an older version to latest version of GSI, it still have some issues. Then in later 2016, it was decided to move to the model system from a older version is IFS to NOAA's GFS model, which is also openly available. Then in 2017, the main goal is to produce a interim product for 10 years from 2007 to 2016. So that's we call this 10 years, the CRA interim, this 10 years product, using GFS spectral truncation 574, about 34 kilometer, 64 levels at the model top, about 0.2 meter bar. So data simulation, the model is kind of based on a 2 years older version of GFS. And data simulation is GSI 3D VAR FGAT type technique. That's for some interim product for the cheaper, quicker run, 6-hour time window. And some new capability is used like for variational bias correction for aircraft temperature observation. And the observation, the radio sound basically based on this CFSR plus some Chinese observations with more vertical levels. And the radio sound temperature also applied some this so-called RAB bias correction. And aircraft observation from the combination of CFSR Met Office and NMIC's own collection. And some retrieved data that use some reprocessed observation like satellite track wind and surface scatterometer, ocean surface wind, and GPS radial occultation data. But satellite readings mostly are from CFSR and the GDAS observation data feed. And for this 10 years of production is recently just finished in the about a month ago. And so we run this production in 5 streams. Each stream is 2.5 years, with half-year overlap between 2 streams. So there is a separate land reanalysis that's based on this NASA LEAS system, land information system, with NOAA 3.3 land surface model, Currently, there is no soil data simulation yet, but just using some forcing data for precipitation, radiation, salt wave radiation, and surface P temperature, wind field, etc. So for some more detail about observation processing and land surface reanalysis, please see some two posters. So here is a table of observation used, this satellite readings observation. Pretty much mostly almost all readings data from CFSR GEOS was used in this interim product, this level 1B readings, and this reprocessed data set AMA. So we collect US data from University of Wisconsin, METOP data from METOP and the UMISAT, European satellite from UMISAT, and GMS from from GMA. And the GPS RO data reprocessed is obtained from Yucca Cosmic, this CDAC data processing center. So here, okay. So because the product is just very recently is finished, the very preliminary diagnostic validation is done. So here is some averaged over maybe half-year period of O-B, O-A statistic. The right curve is from this interim product, this O-B, O-A, and this pi-ESR minus arrow. The right-hand side, that's the number of observations used. The right curve is the number of observations used by the CR interim, because there are some more observation in China region with more vertical levels. So there are some slightly more observation used. If you look at O-A, also the curve overlap with this CFSR observation minus ER interim. So that's to compare, even though the observation number is not the same, but give you some indication. So pretty much the O-A is comparable and even a little smaller than ER interim, maybe because some higher resolution. Okay. Okay, there's some also some rough check for precipitation over China region, verify against the surface rain gauge state. That's compared to curves is compared to GFS forecast. That's, we didn't run a long range forecast, just the 6-hour cycling, the short range 6-hour forecast at these 4 times. So, so basically, there is some better performance over China region compared to GFS forecast. The CMA's Climate Center also checked some extreme event. Here is an example for the 2014 heat wave events in July, August. So basically, in the Sichuan basin and also this southeast China, there's some high temperature event, and seems like ER interim missed this high temperature in the this Sichuan basin, and GEOS5, and this interim product produce some better high temperature events for this extreme. There are some time series comparison. We kind of compare those 3 reanalyses to ER interim. We just minus ER interim. For temperature, 500 millibar temperature, and this lower level moisture is comparable between these 3 reanalyses. There are CFSR and the GEOS555. But we have some problem for zero potential height. So that's the reason, afterwards we did quite some check. We found that this is caused by some reprocessed GPSR data. So after we replace GPSR data by CFSR data, we kind of remove this this high bias of this zero potential height, particularly in the southern hemisphere or maybe in the high mountain region. Actually, we dig into a little more. We found that actually this reprocessed data and the CFSR data, this impact height of some vertical coordinate of this data is kind of different between these two, cause some problems. So we dig a little more into this. Maybe we'll communicate with reprocessing center. This we also compared for other with height latitude distribution. For wind field, there's some reduction here, and temperature not make a big difference. So mostly zero potential height is caused by surface pressure problem. For soil temperature, this 4 years mean field in July. It's pretty much this product is similar to CFSR. A little different. There's some subtle difference in in North Africa, Sahara Desert region. And for soil moisture, there's some difference. You can see there's some, but pretty much they are still comparable. So currently, because this is GPSR problem, we are currently rerunning file stream by replacing this data by CFSR GPSR data. Because this redesign is pretty much quick, it could be done in 3 months. We're currently also evaluating the plant release date maybe next year. We're currently preparing for 40 years of production. It's likely use this 4D EMR technique, with maybe higher resolution if computing resource available. So we expect to complete product by 2020. I stop here. Yeah.
There is time for questions.
Yeah, thanks for the nice presentation. I was surprised by these results for the heat wave in 2014. So basically where you showed that you captured the heat wave, but it was not captured in GRA and ERA interim. Do you have some hypothesis for this? And are you maybe integrating some other data?
Not sure. Maybe related to the resolution or yeah, I guess maybe resolution. We didn't check it at ERA5. If I guess we recently downloaded the ERA5. Probably we can check that more closely. Or I don't know if when they make plot, they make some stupid thing. I don't know. Yeah.
Another question?
Yeah, but we do simulate. There are 2,000 stations, surface station in China region, so that's different, a little bit different. Yeah.
Okay. Thank you very much. The next speaker will be Marie Dravion, talking about the CMEMS ocean, global and regional ocean reanalyses.
So thank you for giving this opportunity to present the Copernicus Marine Service. So that is the shorter name for the CMEMS. Okay. You won't count me this time, right? So that's nice. So I may introduce this as a set of global and regional ocean reanalyses. So we are back into the ocean. So there's a problem? Oh, yes, here we go. Thank you. So, as I said, this is about the Copernicus Marine Service. It's in the ocean right now, and I'm talking here on behalf of a large group of people, as you will see in my presentation. So, the Copernicus Marine Service, I will introduce this very quickly. Okay. So it's implemented by Mercator Ocean, where I'm working, but it's based on a large network of many European countries, many producers around Europe, and many products and state-of-the-art operational products for the ocean. And we are disseminating a catalog of observations, reanalysis, near real-time analysis and forecast of the ocean. Blue, white, and green, meaning physical sea ice, physical ocean, sea ice, and biogeochemistry in the ocean. So right now, we are disseminating around 150 different products. All are available from a central web page and service desk. And currently, we have around 7,000 users, not only interested in weather and climate, but also coastal environment, marine resources, and of course, maritime safety. Okay, where do I point this? Okay, so did I skip one or no? Okay, so this is to give you an idea of the 14 different variables, essential ocean variables we are disseminating. So physical variables, sea ice, and also biogeochemical variables, given by models with data assimilation, but also satellite observations, mostly L3 and L4 graded products from satellites, and in situ observations, of course, of the ocean, giving information at depth that are also assimilated in the models. So we have in situ observations from the Argo network, temperature and salinity, and also biogeochemistry in the past, and real-time observational data that come and feed the portal. So we are currently disseminating 16 different ocean reanalysis products. We have regional products, as you see on the map, for the European seas at high resolution, and global reanalysis too. So each center, so the regions you see on the map are produced, the regional reanalysis, as you see on the map, are produced by different monitoring and forecasting centers. All these regions have at least one physical and one biogeochemical reanalysis available right now. In the global area, you have 2 physical reanalyses available because there is 1/4 of a degree daily frequency that is available, and also there is a multi-product based on 4 different reanalyses at 1/4 of a degree that is currently disseminated at 1 degree. In the Med Sea, you have 2 physical products too, because there's one starting in the 50s, and there's a one forced by era and trim that starts in 87. So the current status of these products, they are all focusing on the altimetry era, because we are assimilating in a multivariate way sea level anomalies, SST, and in situ profiles for most of the systems. The biogeochemistry reanalysis starts with ocean color satellite observations. Most of the systems have a resolution less than 10 kilometers, the regional systems. 80% are based on the NEMO ocean model, ocean modeling platform. They all use different data assimilation schemes, such as 3D-VAR, SIG plus 3D-VAR bias corrections, or ensemble Kalman filter. 80% of these assimilate SST, SLA, and in situ, plus sea ice in regions where it's where there is sea ice. And 30% of the biogeochemistry reanalyses currently assimilate ocean color observations. So what we are aiming at, really improving this as having a very consistent set of ocean reanalysis at high resolution for this marine service, really still focusing on the altimetry era, but improving the resolution below 5 kilometers for the regional models. We want them to have to make optimal use of the observation network, to be consistent with the real-time analysis systems, to have data assimilative biogeochemical reanalysis forced by the physical components. We want to agree on the validation metrics. This is already the case, but we want to go on sharing these best practices. And we want also, of course, to improve to have a maximum consistency between regions and also maximum cross-use of the products so that they are really getting more and more consistent. So that's what we are currently working at. And we are currently beginning a new phase next year to improve this. So you will find these also on a strategy document that we have prepared and we disseminate on the website. So the idea is that these reanalyses are really a reference for real-time applications. And this is to give you an idea of which centers are involved in the production of these reanalyses for each of the monitoring and forecasting centers. Of the 7 monitoring and forecasting centers, you have a lot of people working here. The global center is led by Mercator Ocean, but also involves people from, for the reanalysis part, people from CMCC, Met Office, and ECMWF. In the Arctic, the NASC leads the Monitoring and Forecasting Center. In the Northwestern Shelves area, it's the Met Office. In the Baltic, it's the DMI, and the reanalysis is produced by SMHI. In the, sorry, where am I? 4, 5, 6. Sorry if I forget something. In the Black Sea, IOBAS leads the Monitoring and Forecasting Center, and the reanalysis is produced by CMCC. In the EB area, it's Puerto del Estado from Spain, and the reanalysis is produced by Mercator. And in the Med Sea area, it's the CMCC leading the Monitoring and Forecasting Center. So using these reanalysis products, we've been preparing what we call the Ocean State Report. There's a first issue that was out at the beginning of this year. So it's the work of 80 scientists from more than 25 European institutions. It's peer-reviewed in Journal of Operational Oceanography. And it's based on our products, but also on products prepared by CCI with the GEOS standards, climate quality reanalysis and reprocessing products that we also disseminate in CMEMS that are really complementary. And there's a second issue of this report that is currently under review. So this is just to show you an example of the validation we make for this ocean reanalysis. Here is validation within independent current meters from the TAO array in the Indian Ocean and Pacific Ocean. So you see 3 different moorings, and in green it's an old version of the 1/4 degree global reanalysis showing the zonal currents. And you can see that there's an improvement in the current version, currently disseminated. So we try to, of course, continuously improve the products. And the currents is still an issue in the tropical Pacific. It's a very important area for weather and climate, of course, but many other applications. So we really, we still have issues with data assimilation of sea level anomalies, for instance, but we are really improving a lot this kind of issues, and you will be able to see a poster by Garrick and co-authors tomorrow. This is an illustration of the new global ocean reanalysis at 12 degree that is going to be available next year. These are scores of data assimilation of sea level anomalies from starting in 2007. This is 6 centimeters. This is typically the type of score we obtain from our global reanalysis with different satellites starting from JSON 1 and here JSON 2 for this period. And you can see that the near real-time system here has a lower performance than the reanalysis system. And here, the global 12th of a degree gets better. And here, with the new reanalysis of the 12th of a degree, we really have the best performance, better than the real-time system or equivalent, and even better than the quarter of a degree too. So there's a poster by Lelouch and co-authors on this new reanalysis at 12th of a degree. Another reanalysis at high resolution. Of course, the regional products are at high resolution, and here you can see really the comparison between the global reanalysis at the quarter and the regional reanalysis using the same model but different physical tunings on the EB area with higher resolution. And the comparison here is against tide gauges, but it's filtered from tides. But it's the low frequency variations of sea surface height at these tide gauges, and we really get a better correlation along the coast with this higher resolution model, a better tide, better tune for the physics of the area. And here, at this point, we compare, this is depth and time, and we compare the occurrence of zonal jets here in the observations. That's really well captured by the high-resolution system and less well captured by the global system, even if they show statistical performance that is really comparable. This is another example from a high-resolution reanalysis in the Baltic Sea. Their high resolution is really important because you have a brackish water near the surface. This is salinity in the observation and in the reanalysis. This is from the SMHI group. What is interesting here is that they assimilate biogeochemistry observations, in situ observations. So you have the performance against these nitrate, oxygen, and phosphate observations here with depth. And this last example is for the Mediterranean Sea here. What you see the results from the Ocean State Report #1. And here to show you that you can compare a map from the reanalysis as a reference for the surface currents in the Mediterranean, and they compare with real-time a map for year 2015 from the real-time analysis system. So this MEDC MFC is also monitoring and forecasting center, is also producing a reanalysis with assimilation of ocean color observations. And on the very long term, what's interesting here also is that they plan a coupling with a Black Sea reanalysis. Thanks. Lastly, I'll talk very shortly about uncertainty characterization. So we are doing intercomparisons and ensemble products based on the work that's been done with the Ocean Reanalysis intercomparison project. And so this is from the Ocean State Report #2, under review, currently under review. Sorry, no, it's not working. Well, this is the heat content trend for the 700 meters of the ocean, but it's built from a multi-reanalysis product based on 4 different ocean reanalyses, as I already described, plus 2 observational gridded products. And we have overimposed the shading where the trend is significant with a signal-to-noise ratio. So that's an approach that we try to really generalize. So there is a poster on the AMOC and 2 posters, one on steric height and one on temperature, salinity, and currents that use this product. This is also another product for the regions, another initiative from the Northwestern Shelf. And okay, so I'll finish here. So just to say that the reanalyses are not only a powerful tool for monitoring the ocean variables, but also it's an interesting reference for all real-time applications. So that's why we have to go toward high resolution and consistency with real-time observations. We want to favor intercomparison ensemble approaches, and we want to go towards higher resolution, more assimilation of ocean color. We're going to disseminate reanalysis for waves, and there are many challenges in the future that will be tackled in partnership with the climate service, of course, because we are working on the ocean atmosphere, wave, ice coupling, river runoffs, extension in the past, climate monitoring. So that's a partnership that we have to develop. So thank you very much. Just to finish. Thank you. Just to advertise this cost action.
Quick question.
Thank you. As you mentioned it in your last slide, are those data or those reanalyses be available within the climate data store of the Copernicus Climate Change Service, maybe in the future? Or?
There is no opposition to this, to my knowledge.
All right, we're going to stay in the ocean with CMCC, Global Ocean Reanalysis, with Andres Storta.
So first of all, I want to thank the local organizer to give me the possibility to talk about the CMCC Ocean Reanalysis, and even more because they organized the conference in my hometown, which is quite nice. So I will try to speak about some challenges of ocean reanalysis we encountered in our production, and a short overview of our product. In particular, I would like to mention that the main goal, at least for which is transversal to all their system components, is to produce a reanalysis which provide a 4D state of the ocean, which preserve temporal homogeneity, and this requires to avoid drift, systematic biases, and spurious variability. And the crucial challenge, in my opinion, is that we are using anyway very high-frequency tools like data simulation that corrects at daily frequency, for instance, the ocean state, while we want to capture low-frequency variability. So I think we shouldn't be shy to use methods that are targeted for analysis, are not shared with necessarily with the operational system. And even more, I think, in my opinion, a possible way is to provide, to have multi-scale data simulation. And for multi-scale, I mean spatial and temporal. A couple of examples from our recent works at CMCC. For instance, here we added in our variational cost function a penalty term that penalized the global oceanic content tendency against Earth energy imbalance data estimated from CERES. And this improved not only the monthly, the seasonal cycle and the monthly variability, but also the vertical distribution of the oceanic content, in particular here the assimilation, the introduction of these penalty terms allows us to, let's say, resolve the hidden energy issue in correspondence of the warming hiatus. Another example is about bias correction. I think like atmospheric reanalysis producers are quite obsessed by observation bias correction. In the ocean, we are more obsessed by model bias correction. And even with, I think, many simple formulation, in particular at CMCC, we use a formulation for which in the model tendency, we had a forcing term given by the bias, where the bias is estimated against some reference data set. But anyway, this bias correction consider low frequency spatial scales, 3,000 kilometers in our case, and low frequency temporal scale, 3 months and more, which implicitly include some information on the longer temporal and spatial scale into our analysis. As a justification here, you have the percentage of root mean square error explained by the bias as a function of the time scale. And clearly, it's quite obviously when you go to longer time scale, the bias is dominant. Another challenge of ocean reanalysis, which I called reconstructability, which means even though we are advancing in data assimilation methods, ocean model, atmospheric forcing, and so on, we still have low consistency among ocean reanalysis for some unobserved parameter. In this example is the significance of the allosteric sea level trend compared to the thermosteric. The contour lines show where the trends are significant, meaning that for the allosteric sea level we don't have any significant trend. And another example is about sea ice, where you have the Arctic sea ice extent from an ensemble of ocean sea ice reanalysis compared to sea ice volume, and you can see that there is very low consistency for sea ice volume compared to sea ice extent, because of course it's not an observed parameter. So it's important to understand with dedicated assessment of analysis whether we cannot intrinsically reconstruct some aspect of the past climate, or we will be able to fill a bit this gap with advances in models, data assimilation, and so on. Another challenge, not very exploited, I would say in general, is about validation. So when we are in reanalysis during early periods, we also have very few observations for validation. So in this example, there is our analysis, root mean square error global for upper ocean temperature against non-control experiment. You will see there is a sharp increase in accuracy during the era of Argo deployment. And this is only because the sampling of the verifying observation increases. A possibility, for instance, here is to use a randomization of the choice of the verifying observation, actually for preserving temporal homogeneity of the verifying dataset. And with this method, we find that there is a quite constant accuracy increase with time and not sharp anymore. Finally, another challenge, which I call it cultural challenge or cultural gap, is basically if we compare atmospheric with oceanic reanalysis system, we can see that the resolution is very comparable, and probably in the near future the oceanic reanalysis resolution will also take over the atmospheric one, but still we spend much less in data assimilation compared to the model. Here is the ratio between CPU hours used by assimilation divided by the model for ICR5 courtesy of the Copernicus Climate Service Help Desk, compared to our system, which is based on 3D VAR, where we spend 16 times more in the ocean model than in the data assimilation. This is just an example, depends on the configuration, but it's quite typical of ocean reanalysis, which do not use very advanced data assimilation schemes, even though the tools are already in place or being developed. And I think in light of the efforts for Earth system reanalysis, this picture should change in the future. Very quickly, an overview of the CMCC reanalysis. Here we started more than 10 years ago, updating the data assimilation from optimal interpolation to a variational system, which allowed us to assimilate in an easy and sensible way altimetry data. I don't have time to go into details. Thanks to MyOcean, we increased the resolution to 1/4 degree and also start assimilating ice concentration data, which improved the representation of low frequency signal in polar areas. In this example, there is the sea ice motion speed linear trend, decadal linear trend, is from estimated from satellite, and to experiment with and without sea ice concentration data assimilation. With V4 of our reanalysis, yes, we introduced the bias correction I shortly introduced before, and the retuning background error covariances. But in this version, we also provide quite deep assessment of the impact of feature simulation component on different metrics like skill score, low frequency variability, and transport. In this example, how the observing network impact the eddy kinetic energy, where in black is the reference data set. In orange there is our analysis, and with the green and blue you will see the impact of respectively altimetry data assimilation and in situ data assimilation on the increase of the mid-latitude eddy kinetic energy. With V5 we introduce some constraint on sea ice thickness and also some flow-dependent inflation of the background error covariances using the data assimilation to account for the different observing network along the reanalyzed period. In this picture I just make as an example that without a constraint on sea ice thickness but only assimilation of sea ice concentration, there was some quite severe spurious variability of sea ice volume. We have another reanalysis called V6, which is mostly used to initialize our seasonal prediction system. So it introduces stochastic physics in the ocean, plus perturbation of atmospheric forcing and observation to provide 4 members for the reforecast and 8 members for the real-time reanalysis, just targeted to initialize the seasonal prediction system. Latest release of our analysis, V7, we increased the vertical resolution to 75 vertical levels, update the NEMO, and introduce variational quality control of observation. With this version, we really improve a lot of transport, I would say in general. In this example, the MOC low frequency variability from V7 in red is compared to the rapid estimates in black and the previous reanalysis in blue. With this new update, we really improve both the variability but also the mean state of the MOC in this case. Another family of products is the historical ocean reanalysis, which cover the entire 20th century. For this kind of exercise, the representation of the long-term variability is as important as the characterization of the uncertainty, and to do that we use 4-member reanalysis where we combine 2 different atmospheric forcing, in particular 20CR V2 and ERA 20C, with 2 methods to assimilate SST data, while in situ are always assimilated. There is a dedicated poster on this. Anyway, in a few words, if you look at the global oceaning content in the top 700 meters from the ensemble of reanalysis, black against the ensemble of control experiment without data assimilation, we can see that even in early period with a few observations, our reanalysis approach is able to shape the its content So a brief outlook into the future is the 116 ocean reanalysis, whose production will start soon and will include, will cover a short period from 2010 to 2016, but still quite a big effort and unprecedented resolution, which will allow us to study the contribution of the eddy activity on the ocean energy at global scale. I just try to advertise our analysis that can be downloaded through FTP. There is a possibility to register at the website. Of course, data are free. I just want to mention that based on the atmospheric reanalysis practices, our ocean reanalysis and comparison practices, we start to disseminate not only the reanalysis data, but also data from control simulation without assimilation, climatology data, analysis and bias correction increments that can be used for budget analysis and things like that, and data also for interpolating to regular and easier grid. Before concluding, I also would like to advertise the evaluation of ocean synthesis construction that there is a poster from IDA explaining and summarizing these efforts. And thank you for the attention.
We have time for a question.
We are moving towards coupled reanalysis, NCEP, JMA, we are all moving towards coupled reanalysis. So how do you see your activities, or the activities of people doing just one component reanalysis evolving?
Yeah, I mean, I think it's an important exercise to understand the optimal methods for one component. Also, probably it's important to couple reanalysis will compromise in terms of resolution. So I think one component only reanalysis may still serve the purpose to reanalyze all the period at, of course, higher spatial resolution. So I think they are complementary efforts. I guess will be quite long way before a couple analysis can have the same high resolution and a component only.
All right, the final presentation of this afternoon session, this session does continue on tomorrow, is on the ERA coupled reanalyses with Dinan Scheppers.
Thank you very much. Yes, so I've heard many talks today already mentioned the coupled reanalysis, and mostly was in the future plans. Well, I can now introduce to you a data set that exists. It has been produced in the ERA-CLIM 2 project for the last 11 months. So in that sense, you can say the future is already here. And so I will just see if, yes, there we go. So just to start off with a reassuring message. So there's future plans to go towards coupling, and at the European Centre, they are very aware of the added benefits of moving towards a coupled system. And just to quote the roadmap, the 10-year research plan is, while the Earth system modeling is already in its early stages, the application of a simulation in a coupled system could be groundbreaking. So it's a very reassuring thought that the operational weather forecasting community is actually behind us, which is a force for good. So the Earth system modeling that's already in its early stages one of the exponents of it is the single executable coupled model that was developed at the European Center, where you have the IFS, which is the atmospheric model, the wave model, and the ocean model, which is NEMO, integrated in one executable, and every time step they are exchanging the relevant variables at their interfaces, which is basically the single. It's an important part of an assimilation system. So if we take this coupled model and we integrate it into an assimilation system, and Adrian already showed this plot, combined with the assumption that somebody would explain it later today. Well, this is me, challenge accepted. So now I've collapsed the coupled model into a simple box, and you see the coupling actually takes place here with a coupled background forecast. Then the assimilation is done in either IFS or NEMO in 4D var, 3D var, and the separate increments are combined in another coupled background forecast. And this is done in 2 outer loops with a final trajectory run at the end to make an analysis that's consistent between ocean and atmosphere. And in the end, you end up with all the consistent reanalyses of the different Earth components. So this is what we call outer loop coupling. Coupled to that is also a land surface analysis, a dedicated land surface analysis, which I would refer to as weak coupled. And the only coupling is through a shared background forecast. There is a poster tomorrow by Patricia de Rosnay. She will, where there's more details on the exact land surface analysis system. So now we can complete the picture by adding observations and an SST analysis to force the model at the interface. So for the atmosphere, we have a full observing system, which means the full observing system at the end of last year. In the ocean, we are simulating salinity and temperature profiles in situ and the sea surface height as well from satellites. And as I said, there is an external analysis, SST and sea ice, which is the Ostia product, and it's used to constrain the coupled model at the interface, at the sea surface. And there's a sea ice extent simulation as well in the LIM model, which is implicit in the NEMO. Then we end up with this overview of what the system looks like. So you can pick your favorite detail. I will just mention a few. That it's cycle 42R1, which is April 2016 when it was released. So it's relatively recent. It runs at TL319, which is around 60 kilometers in the atmosphere, 137 levels. And important to note is that the assimilation window is 24 hours instead of the usual 12, as we have in ICR5, for instance. And this is inherited from the Century Reanalysis that were made with the same coupled CIRA system. The ocean also runs on the 24-hour assimilation window. It's a quarter-degree ocean, so it's fairly high resolution compared with the atmosphere. And there's the wave model that you can pick your favorite detail from there. So now, for some interesting illustration of what this coupling actually does to your system. So this is something that my colleague Giovanna De Chiari did, and she has. It's an observation denial experiment. She ran 2 coupled analyses, one with scattering winds and the other without scatterometer winds. And what I've plotted here is the difference in sea surface salinity, basically purely by either denying or the scatterometer winds to your system. And here you see the difference in salinity in the ocean columns. So if we now try to have a closer look at these differences, so we can look at the background departures for in situ salinity observations that are assimilated in the oceans. We see that actually by adding scatterometer winds to the atmospheric assimilation, we increase the background fit of the observations in the ocean, which is a very healthy and nice to see effect. So having a coupled system actually benefits the assimilation. A similar exercise can be done for atmospheric observations. So we can look at the background fit to several tropospheric observations. Here there's the winds from radiosondes and from satellites, and there's temperature. And you see that there is, in the free troposphere, there is basically also a reduction a reduction in error to background fits by coupling to the ocean, which is a very healthy and it's a signal and very nice to see. It's not all rosy though, because if we start to look a bit more in detail when we stratify by regions, in this case tropics, extratropics, and look at the satellite winds, we see that the tropics look very healthy and there is a reduction in standard deviation in the background departures. The extratropics, though, they show a slight degradation here in the lower troposphere, which is so far unexplained, but we need to do more research into that. It's at least an intriguing question of what's happening there, and it will teach us a lot about the system, how it performs, and how we can implement it. So now I have to say a few words about how it's produced, since it influences the product in an important way, actually. So it's produced from January this year, so the last 11 months, and we had to do a trade-off between production times, the time that it takes to produce, because the project is set to end this December, and to produce actually a meaningful amount of data to actually do some research on. So we settled on the following setup of 4 production streams, relatively short, between 2 and 3 years, and only half a year of overlap per stream. So we have half a year for the weather and climate to spin up from their initial conditions and before we have to stitch them. So here, the red bars indicate the different production streams, and they can be stitched together to form an 8-year data set that will be delivered at the end of this year. Although it doesn't end there, because there is the intention to go beyond this, beyond the end of the project. We'll keep as good as we can the production going and in the following way, by first of all extending one of the streams to do some studies on how this spin-up actually works in a coupled system. You can imagine that the atmosphere spins up a lot faster than the ocean. How do we take care of that in future coupled reanalysis? If we want to go to operational reanalysis, how much spin-up do we actually need? We also want to extend the last stream into near real time, so we can make maximum use of the year of polar prediction, for instance, that's now spinning up. So we can have maximum synergy with that. And in the beginning, we'll pre-extend from 2015. So we'll have a 12-year plus data set in the end, hopefully, and that would give us a very nice set to work with and to study and to draw conclusions from for future coupled reanalysis. So not unimportant, how can you access the data? Since we produced it, it's a public data set, we've looked at it, but more importantly, we want you to look at it, the community. So it will be accessible through the normal Mars catalog at ECMWF. It won't be in the climate data store, it's a research data set, it's not an operational quality controlled product, but nonetheless, we would very much appreciate it if you could have a look at it. There will be 3 hourly analysis fields, so unlike the ICR5, which is hourly, there will be atmosphere, sea ice, waves, land surface, will all be there. There's monthly means pre-calculated, so you don't have to do it yourself. The ocean fields will be in that CDF format, but in Mars as well, as part of the project deliverables. And there will be, of course, the observation feedback provided. And this should all be available by the end of the year. So we can go on with some concluding remarks. So as I said, it's a proof of concept coupled reanalysis data set. It's for you to look at, for us to look at. It's to assess the application of the CERA system for coupled data assimilation in reanalysis. We can research the effect of using this system, so we can research the benefits in data assimilation, as I showed. There will be a lot more research going into the benefits of having coupled assimilation to initiate forecasts, for instance. And it will be used internally to aid the further development of a coupled data assimilation system at the ECMWF. And in the end, I tried to make a nice diagram showing that this research being done in Angelicum 2, which is funded in the FP7, will eventually flow into the next operational era reanalysis, hopefully done by Copernicus, which I put era 6 between brackets. I don't know if the era 5 naming convention will just add one number, but it will be the future reanalysis that we hopefully feed in a lot of lessons and new science to make that a better one. So, thank you for your attention.
We have time for questions.
I see two
already. Thank you for your presentation. I got two questions. First, have you compared the CERA data with the CERA 20C? And then can you see some improvement in terms of the ocean increment? The second is that have you looked at the have you applied the ocean bias correction in the ocean data simulation? Thanks.
All right. Oh, sorry. This better be a good question now, I guess. So first of all, thank you. It was a very nice talk, and it's nice to see that where we're all headed is possible. Just a question about terminology, and it's maybe something we should think about in terms of the discussions that follow or conclude this conference. You made a point on a couple slides of mentioning that the land component, you refer to that as being weakly coupled. On the other hand, of course, the minimizations for NEMO and the atmosphere are separate. So that is essentially weakly coupled as well, even though I understand how they're coupled through the outer loops. So are you making a distinction between two types of weakly coupled, or are you're not calling that IFS NEMO weakly coupled?
I will first go back to his questions if you don't
mind.
Oh,
I'm sorry.
Yeah, the microphone didn't work, so you didn't get to answer them. But so your second question is easy to answer. We didn't apply the ocean bias correction. Your first question is also easy to answer, but it might not be the answer you're looking for, since the production is ended last week, actually. So we didn't spend a lot of time researching really the data set. We'll have a look at it. At this moment, I can't tell you. Sorry about that. So now, to your question, so the terminology I put in the slides was not meant to as a general proposal of terminology. It's more to I know, by the way, that there's a white paper being written to actually, or has been written to propose a fixed terminology for different ways of coupling. I was just trying to distinguish between the fact what I call outer loop coupling, where you have a combined background forecast, and you also apply the increment in a combined way in the second trajectory and the third trajectory. That's a stronger way of coupling. It's not strongly coupled, as you would say, with combined covariances, but it's a stronger way of coupling, as that the land data assimilation is coupled to the system, since it's only coupled by the first background forecast.
Hi. Sorry, I may have missed this. Is there a vision that you would have a coupled 4D VAR system for the ocean and atmosphere?
Not immediately, no. I think the vision right now is to stay with the outer loop coupling system, thoroughly assess it, investigate it. But there is, in the operational weather forecasting divisions, let's say, they are looking at moving towards a more coupled 4D VAR. But it's very early stage yet.
Just a quick question, since it's rather late. In this system, what is the cost ratio of running the atmosphere system compared with the ocean system, both for assimilation and model? And if the ocean is much cheaper, could you consider to have a one-way coupling for the spin-up if you need a long spin-up for the ocean?
Yes. Yeah, I guess we could consider it, yes. I'll have to think about it in more detail, what that would mean, but it's a good suggestion. Thanks.
Only a second. It seems that I see in one of your first flow chart that in the down there was a radiation, solar radiation. Very
here.
No, yes, precipitation. Later on, it completely disappeared. In the solar radiation, the effect of the solar, according to the five solid of Platon philosophy, we should put on overall models, we should put the effect of the sun. But I haven't seen all the day no effect of the sun going on. This is the first slide in which I see solar radiation, and later on disappeared completely. That's all. I would like to know why.
Okay. Well, I believe this mention of solar radiation has more to do with cloudiness in the atmosphere, so the analysis of cloud fields and downwelling surface radiation, than maybe the solar radiation you are referring to. But
all right, so that's it for today. I want to thank the speakers for doing a wonderful job of excellent material and staying on time. I'll take the blame for any overages. So thank you very much, everyone.
So now we have icebreaker till 7:30. Tomorrow morning we start at 9 sharp. And for the Scientific Organizing Committee, if we could please meet at 8:30 in the Sala Colonna tomorrow morning, so that we can have a brief chat about how things are going, whether there is anything we need to plan and so on. So we move to where we were for coffee, for drinks and some finger food. Thank you very much.